What?
All right, section 5.2, finding the real zeros. So this section, we're not going to find the complex zeros. When I say real, I don't mean they exist. They do exist, but I mean real numbers like not having an I involved. So we're not going to worry about the complex numbers in this section. We'll do that in the next section. So the skills that we use, though, to find the real ones are going to be the ones that we need to find the complex ones also. Okay, so one of the things we're going to utilize, and it's not so important that you memorize this algorithm. My wife and I have a joke at home. I was doing tutoring last year, and had a student who was in there for tutoring in geometry, and he had a Rubik's Cube, and he was sitting there just flipping and turning the Rubik's Cube, and I said, wow, you're fast at solving that. He said, yeah, it's just algorithms. And I said, what's that mean? He said, oh, it's just patterns. And I said, well, you know, an algorithm's math, right? And he said, really? And I said, yeah. I said, if you'd spend as much time doing your geometry as you would do those algorithms for solving that Rubik's Cube, you'd probably be passing geometry right now. But so we laugh about it. Anytime we see the word algorithm or a Rubik's Cube, we say, oh, it's just algorithms. We're going to utilize division here. So we're going to take two polynomials and divide them. We'll call one of them a function f of x and the other one a function g of x. And when you divide those, whether we use long division or synthetic division, it works out to where you have this quotient function plus the remainder function divided by what you divided by. Okay? It's really, it's just, we get a quotient, q of x. Anytime you do division, you're going to get a quotient. Remember, that's the name, that's what they call the answer to a division problem is quotient. And then you get a remainder. Sometimes your remainder is 0. Sometimes your remainder is a number. Since we're dealing with polynomials, sometimes your remainder is like x plus 4, something like that. So your remainder can be different things. Your g of x, when you write that, this is basically, when you were in junior high or elementary school and you had this fraction 11 over 2, a lot of times you did mixed numbers. When you did that division, so 2 goes into 11 how many times? 5 times. And then you had how much left over? A half. Really, that's 5 1/2 is 5 plus 1/2. That's what that is. So we're just doing it with polynomials now. So we're just taking it to a more high school, college level for us. Okay. So that's really all that means is we're taking two polynomials, their functions in our case, and dividing them. We're going to get a quotient, and then we're going to get a remainder. Possibly that remainder is 0. There's some special things that happen when that remainder is 0. So that's what we want to happen, and that's what our goal is today. All right, so let's first work on our skill of long division. Okay, we're not going to use long division every single time. We're not going to use long division a ton, but we do need to know how to do that for some stuff that's coming up later on. All right, so that's why we're doing long division. We'll do a couple examples of long division, and then we'll do synthetic division, which is what we'll use most of the time anyway. Okay, long division is very useful if you're not dividing by a linear function. If you're dividing by a quadratic or something like that, long division is what you have to use. So it's easiest to show, though, using linear pieces. So let's divide. Divide f of x is x cubed minus 4x squared minus 5 by g of x, x minus 3. All right, so this is our first example. We're going to use long division first to do this, and then we're going to do it with synthetic division. Okay, and I'll show you how it yields you the same answers out of that. So long division, we're going to divide those two. We're going to use the old long division symbol from elementary school. Been a long time since you've done that. Well, probably not. You did long division last year in Algebra 2, I hope. We're going to divide by x minus 3, so that's going to go on the outside. On the inside of there is going to be our f of x function. And one of the things when you're doing either long division or synthetic division, you've got to be careful about is that you need to make sure there's a representative from every power of x, starting with the highest one. So there's an x cubed. There's a minus 4x squared. Yeah, plus a 0x. And then minus 5. Technically, it doesn't matter if you put minus 0x. I just put a plus because who wants to put an extra minus sign in there? Makes it more confusing if you do that. So, all right. You remember long division from in the past? You look at the x. What times this x would give me x cubed? X squared. So that goes up here. And then we distribute the x squared to both of those terms. So x cubed minus 3x squared. And then I put mine in parentheses and put a minus sign out front. That way I know I'm subtracting this stuff from the two terms above it. X cubed minus x cubed, that's going to cancel out. That should cancel every single time. Okay, so that's canceling out. And then we have negative 4 minus negative 3. It'd be negative 1, right? Yeah, negative 1x squared. I like putting the 1 there. And then I'm going to bring down the next term. It's a 0x, but I'm bringing it down anyway. Okay. If you're dividing by something larger than this, you're going to bring down ever how many terms you need to make that the same thing. So if this was a trinomial here, you go ahead and bring down the third term too. But usually you only have to bring down 1. What times x gives me negative 1x squared? Negative x. So I'm going to subtract x. So that'd be negative 1x squared and be positive 3x. And I'm going to subtract that stuff. And the x squareds cancel. 0 minus 3 be negative 3x minus 5. Then bring down the minus 5. What times x gives me negative 3x? Negative 3. Distribute negative 3x plus 9 and subtract. These cancel. Negative 5 minus 9 be negative 14. That is the remainder. Okay, so we would write plus negative 14 over x minus 3. And there's our quotient and remainder of that. That's the division algorithm. Here's our quotient. This is our remainder. That's what we're building out of that. Okay. So using long division, we can get this polynomial answer out of that. We can get the same polynomial answer using synthetic division, but we don't have to deal with the x's and stuff in synthetic, which is why we like it better. Okay, so with synthetic division, let's do that same division, same problem. F of x is again x cubed minus 4x squared minus 5 g of x is x minus 3. Okay, find f of x over g of x. Divide those two is what I'm saying. Okay, so when you do synthetic division, not sure exactly how Coach Mack set up his little synthetic division. I'll show you how I do it, and there's several different ways to write it. But I do this. I make this big L bracket here, and I put a little shelf out here on the side. I'm not sure if that's how he writes his or not. It really doesn't matter how you do that, as long as you organize yourself. Now, inside on the top row here of the bigger box, we want the coefficients of our polynomial we're dividing into. So that would be a 1, negative 4, 0 for the x that's not there, and then a minus 5. Up on the shelf, though, we're dividing by x minus 3. So we don't put a -3 up there. We think, okay, what's x minus 3 equal to 0? It'd be x equals 3. So it's a positive 3 up there. So it changes signs, basically, is what you can look at that as. I show the set it equal to 0 because what if it were dividing by 2x plus 5, something like that? Then it's a fraction that's going to be on the shelf. So. Now, with synthetic division, the first step is add straight down. There's nothing to add the 1 to, so you just say 1 plus nothing is 1. And then you multiply. 1 times 3, 3. And then you're always going to add the column. So -4 plus 3, -1. Then multiply -1 times 3, -3. Add. Multiply. This number hanging out on the end, that -14, guess what that is? It's your remainder, just like it was when we did it with long division. 3, yeah, this -1 right here times the 3 got me this -3. And then I added to get that. And then what that does is gets us this polynomial. Anytime you do synthetic division, you're going to be dividing by something that's linear. The degree of a linear term is how much? What's the degree of x minus 3? 1. Look at that. It's got there's not an exponent there. There's like a 1 that's written there. Okay. So it takes the degree down 1. So we started with an x cubed function. We did synthetic division once. It takes the degree down 1. So this is now x squared minus x minus 3 plus -14 over x minus 3. This is our division. That's what it equals, which is exactly the same thing that we got when we did it with long division. Just didn't have to deal with all the x's and the distributive property and all that stuff, which is the nice thing about synthetic division. It really works well, but it only works with linear things that you're dividing by. Long division, very useful when you're dividing by something that's quadratic or larger. Synthetic really works well for linear terms. Doesn't work well at all for quadratics. Okay, so we want to use it for linear terms. Okay, let's get to the rule that we want to employ here. This is what's going to get us finding those zeros, and that's the factor theorem. X minus something, we'll call it C, is a factor of f of x if and only if f of c is equal to 0. Okay. If and only if is a pretty strong statement in math. That means it goes both directions. It means it's really a strong argument that if x minus c is a factor of some polynomial, then if we plugged in just plain c into that polynomial for x, it'll get us 0 as an answer. If it's a factor, then that helps us find zeros out of that. So what we want to do is test a few things here with synthetic division inside, because this is a linear term, right? It's a linear factor because it's just plain x. We can use synthetic division to test to see if something is a factor or not. Okay, so we want to test, this example C, is x minus 1 a factor of f of x equals 2x cubed minus x squared plus 2x minus 3. Okay, so we're going to use synthetic division to help us factor that larger polynomial. We could try grouping if we wanted to with that polynomial. It doesn't work. So this is where synthetic division is going to help us break down a polynomial. So let's use synthetic division to test that out. What's going to go on my shelf? Positive 1 or negative 1? Positive 1. And then I have my coefficients next. Make sure you got a power from each representative of x. So 2, negative 1, 2, and negative 3. So there's cube, squared, plane, no x's. Okay. And then run your synthetic division through there. So 2. You get a remainder of 0. If you get a remainder of 0, then that means it is a factor. Okay. Means x minus 1 is a factor. If you get anything else there, it's not a factor. Okay. So we could actually write the factored form of that polynomial. That f of x is actually, could be written x minus 1, and then what's our quotient here? It's 2x squared plus 1x plus 3. That we can use that factor, and this is our quotient. The 2x squared plus x plus 3 is the quotient that we got when we did our division. What we're going to do is utilize that further and further to get to where we can maybe write it as all of the factors, like factor it completely using that. Once we get it to quadratic, we've got some better skills for factoring. We use that x method if it would work. If we're looking for zeros, we can use quadratic formulas. Those sort of things can help us here, but doesn't necessarily. Zeros don't have to be pretty numbers all the time. So that's what we're going to realize as we go a little further. All right, let's look at another one. Let's say we had f of x equals 2x cubed plus 11x squared minus 7x minus 6. Okay, and we want to find all the possible rational zeros and then factor f of x. Okay. Now, the possible rational zeros, there's this rational zero theorem. You could read the whole thing in your book if you want to. But the rational zeros theorem is basically taking and narrowing down, instead of having all the numbers from negative infinity to positive infinity as possible answers to this, we're going to narrow it down to a set that is dependent upon the leading coefficient and the constant term. Okay, so what we have to do is look at what I call P over Q. You may remember this from factors of P and Q. P is the constant on the end. Q is the leading coefficient. That's what you want to think about. P is the constant on the end. Q is the leading coefficient. So the factors of 6, we don't worry about the negative. You're always going to have plus or minus because, a factor of 6. What are the factors of 6? 2, 3, 1, and 6, right? I'm going to write a 1, 2, 3, and 6. Positive 1 goes into 6 just like negative 1 goes into 6. So the plus or minus is always going to be there. Okay. Technically, it's plus or minus on each and every one of those, but instead of writing it out like that, I'm just going to put plus or minus in front of the whole fraction. And then, what are the factors of 2? 1 and 2, right? Technically, it's positive 1 and negative 1, positive 2 and negative 2. Okay. Now, what that narrows us down to is a small list of a few numbers that it could be the zeros of this polynomial. So we divide all of the numerator, each number in the numerator divided by 1, and then each number in the numerator divided by 2. So that'd be 1/2. 2 divided by 2 is 1. I already got that one. 3 over 2. And then 6 divided by 2 is 3. And I've already got that number. Though I've narrowed it down from all the numbers from negative infinity to positive infinity down to 1, 2, 3, 4, 5, 6, technically 12 numbers are the only possible rational zeros for this. What's it mean to be rational again? It means it's a number that can be written as what? As a fraction. Okay, so we're talking about rational zeros, talking about the answers that can be written as fractions. It doesn't help us when we go like if square root of 2 was a 0 to this polynomial. It doesn't help us find that, but surely some of these will work, and that'll help us be able to break that bigger polynomial down. Okay, so this is kind of the steps that we take. So know how to find that. You're not going to have to check every one of those. When I was in school, we didn't have the graphic calculator quite as readily available to all of us. There was a teacher here that had a set of 10 TI-82s back then. And so we didn't get to use them every day, and she didn't have enough for every student. So you guys are living in an age of prosperous mathematicians that you don't have to check every one of those. We had to check every one of those by hand. You got a graphic calculator, that's going to help us. Okay, so this is what you're going to do there. You're going to take that original function, and we're going to graph it on a graphing calculator. I'm going to go to y equals. Make sure your plots are turned off. You're not running any kind of app that's going to mess things up. And type in that function, 2x to the third plus 11x squared minus 7x, and then a minus 6. And you're going to graph that. And we should see some places where that is crossing the x-axis, right? No, those are important. Those are the zeros of that, which is going to help. That the zeros are going to help us factor that polynomial, which is what this problem asks us to do. So when I look at that, I try to look for good numbers. Here, reading it left to right, here's a pretty good number. It looks like it's going straight through one of the points. What is that point? It's -6. I can verify that by hitting trace and then just type in -6 and hit enter. Oops, not plus, but hit enter. Does it give me a 0 on y? Yes. Then that means that's one of the numbers. That's the first number I want to try with synthetic division. Okay, that's what I want to do. So let's take that 6. -6 is in our list. Those numbers should be something in our list. If we're going to use them in synthetic division, it should be a number that's in our list of P over Q. -6 is in that list. So I'm going to set up my synthetic with a -6 on the shelf. And then I've got 2, 11, -7, and 6. And I'm going to run synthetic division with that. Did I do that? And that's supposed to be a -6 right there, isn't it? I didn't copy that down right. 10. There we go, -6. And then we get +6 right there. And there's my 0 in the remainder. Okay. What that tells me is that x plus 6 is a factor. Why did the sign change? Because it's opposite. Yeah, whatever our number on the shelf is, it's the opposite of what it is inside of the factor. Okay, so far we've identified one factor of the polynomial. We've reduced this down to a what? What started out as x cubed. Now the blue part here is x squared. So we've reduced it down to a quadratic. Could we use the x method to find the other two factors? Yeah, that's what I would do. I mean, I'm looking at that saying that's 2x squared minus x minus 1. And if I factor that, Be -2 and -1. Be -2 and +1. So I could factor that as 2x squared minus 2x plus 1x minus 1, and then group it. So I get the factors then, 2x plus 1 and x minus 1. And then I had the factor that I found earlier, was x plus 6. That's the factored form of f of x. That's what I wanted. What if I ask you, what are the zeros of f of x? How many should there be? There should be 3, because what was the degree of the original problem? 3. So there should be 3 zeros to this thing. Set each one of those factors equal to 0. Yeah, and then the 2x plus 1 gets you a -1/2. And then x minus 1. X equals -6, x equals -1/2, x equals 1. What I want us to do is tie that together with that graph that we drew, or we had our calculator draw. That number right there, what number is that? -1/2. That number right there, 1. That ties together with the zeros we found by factoring. They should match up. Okay. When they're all real zeros, then that's what will happen. You can get those that way. The factored form, run a synthetic until you get it to squared, till you get the polynomial down to a quadratic. Then we should be versed enough in factoring quadratics that we can factor that, if it will factor. All right. Let's look at another one. Got about 5 minutes before they're going to call seniors to go on the trip. So that time changed from what it was the other day. So x to the 5th minus x to the 4th minus 4x cubed plus 8x squared minus 32x plus 48. All right, so a big one. It's got an x to the 5th power. Okay, we want to find the real zeros. Find the real zeros. I'm going to go ahead and tell you this one has a couple of zeros that are not real numbers. They're imaginary. Okay, so we're going to find the real ones. This section is only about the real zeros, not the complex ones. Okay, so we just want to find the real ones. All right, so I want you to tell me what our P over Q list is. So what goes on the top of our P over Q list? The factors of, this is P, this is Q. Factors of 48 go on top. So the factors of 48, 3 goes into it, 4 goes into it, 6, 16's in there. 16 times 3 is, yeah. And then 24 times 2, and then 48. And then on the factors of Q, that's easy, 1. So it works out, it's a pretty big list, but I mean, you're dividing them all by 1. So you really just have the numerator there that you're dealing with. Those are the possible zeros to that. So we want to run our synthetic division with one of those. Okay, so we want to find which one of those to start off with. So say that again. Would it be? How do I know which one? You're saying x minus 1 is a factor? That number right there? How do you know what number to put there? No, not always going to be Q. It's going to be one of those out of that list. that -6 we used on the last example just happened to be the same number as q. It's not always going to be q. What do we need to do to find a number that'll work here? Graph that thing. Graph that polynomial. Don't just kind of by luck of the draw pick one. That's what we used to have to do when I was, we had to just, okay, I'm just going to guess that it's 3 and try to see if that worked. And if it didn't work, I try a different number. And then if it didn't work, I try a different number. Okay, so yeah, it was a long process, but you guys have some nice tools to use here. So, and this is a pretty large polynomial, so 5th degree is pretty big. 4x takes a while to type in. Even plus 8x squared, 32x plus 48. Hopefully, some numbers jump out at us when we see this graph happening. I didn't type it in right. I didn't type it in right. Yeah, it should be a minus sign, and then a delete that button. And now it should be better. I know what the answer should be. So. Oh yeah. Yeah. Now, looking at that graph, what do we know about one of these zeros? This one goes through. -3 is one of them. It crosses the x-axis. What about this? 2. So it's got a multiplicity that's what? Even. So we know it counts either twice or 4 times. You can't tell which until you try. This is what you know there. But we know this has a multiplicity of 2. What that means is you can use it twice in synthetic division. Okay. So you got a -3. Let's just start with that one because it's the one that goes through the x-axis. So we'll start with that in our synthetic division with a -3 on the shelf. 1, -3, 12, -24, -16, 48, 16, -48. All right, so zeros. X equals -3. What's the factor that goes with that? X plus 3 would be its factor. Okay, so that helps us. Now, we're going to take that quotient and we're going to do synthetic division with it. Okay, we're not going to go back to the original. We're trying to break this polynomial down as far as we can. So we're going to do synthetic division again with a different number. What's the other number we're going to use? 2. So I'm just going to put my box here and put a 2 on that shelf. And then I'm using these as my coefficients. Pull the 1 down. It's 2. -2, -4, 4, 8, -8, -16. What do you know? Remainder of 0. X equals 2. Be x minus 2 would be your factor that goes with that. Okay. But we saw on the graph that bounced off the x-axis. So that tells us that this thing that particular 0 has a multiplicity that's even. So we're going to run the 2 again into this quotient because we know it counts more than once. The odd multiplicity is hard to figure that out about. But when you see it bouncing off the x-axis, it's obvious you need to run that again in synthetic. So we're going to run that again because so far we've only broken this down to x cubed. Started as x to the 5th power. We did synthetic once. That got it to the 4th power. Did synthetic again. That got it to the 3rd power. If I run that 2 one more time, what's it going to turn it into? Squared. And then we got tools to solve squared problems. We know a lot about quadratics. So I'm going to run synthetic one more time with that 2. And again, the reason I can use that too is because right there it's bouncing off the x-axis, so we know it has a multiplicity that's even. Again, odd multiplicity, you really can't see it because odd multiplicity is going to do what with the x-axis? It's going to cross it, go through it. Even multiplicities bounce off of it or touch it. So run that through again. If you try to run it through and you don't get a 0 as the remainder, then it doesn't work. Okay, so if you think, okay, well maybe that -3 had a multiplicity of 3 or something like that. If you tried -3 again, it won't work again in the remainder. The quotients there.
At this time, we're going to begin calling seniors to load buses for college and career fair.
All right. So we get x equals 2 again.
We'll load the front bus. So get on there as quickly as possible. Caleb Anglin, Tyler Atherton, Tanner Atkins,
all right, so
Harriet Nara,
you could get those answers. They're not real numbers. We found all the real ones. -3, 2, twice. 2 with a multiplicity of 2. These, if I solve that quadratic, it's going to be plus or minus 2i. That's section 3. All I want you to do is the real ones in this. So you're going to break that polynomial down with synthetic as much as you can. All right. Page 357. 39 through 72. That's what I want you to work on.
Danae Grisham, Joseph Hager, Jared Harville, Peyton Holt, Carson Hopkins, Braden Horton, Macy Johnson, Alyssa Jones, and Trevor Jones. Load bus 1, the front bus.